Okay, so as you're playing with this, let me ask if anybody has questions from last time. They want to make sure that we cover today. Okay, then I'm going to ask you to consult with your group mates and discuss what you're doing with the phone to see if you can come to a consensus about how you're able to determine whether there's a positive or a negative charge somewhere.
There are red arrows pointing away, negative red charge in the middle, and that red charge is positive. And if there's a blue charge, but you're between where it's a negative charge.
I've got some charge distribution. You come on up. So let's take a rod with a given length, or give you a surface of some area. We have some charge, we have it spread across some length, surface, or volume. And what we're basically going to say is that if we want to isolate a little piece of the charge, and the charge is uniformly distributed, the fraction of the charge contained, the fraction of the entire charge contained in that chunk, is equal to the fraction of the entire length contained in that chunk. So this length is dx, and the entire length is L. That's the fraction of the rod that is contained in this volume. If it were a surface, we would have an area, dA, and some total area, A. And then this would be dA and A. This is what you're pointing at, that's the charge. So you're calculating, say, the electric field from this point, for that small volume that acts like a point, it's so small. And then the integration happens by adding up all the points along the rod or along the area. I think you find the angular because the line charge
but you can always
Okay, so as you're exploring where you think the charges are and whether they're red or blue, positive or negative, if you want to check your work, you can turn your phone upside down and they will appear. So you have to generate a new charge distribution before they disappear. So that trick's not going to work until you get past the first example. So while you're doing that, I'm just going to start with our introduction today. What we're seeing here is a different way to think about electric fields. in chapter 5, we talked about point charges producing electric fields. And now what we want to do is sort of work in reverse. We want to say, if there's an electric field, can we infer the existence of a point charge? So we're working backwards. Okay. Sometimes that's a really useful thing to do. Other times it's just a mathematical trick that lets us sort of solve a problem from the back forward instead of from front to back. And so we're going to learn a technique called Gauss's law today, or a law called Gauss's law, that's going to use this idea that the electric field around a point charge is closely related to how much charge you have inside that region that you know the electric field around. So we'll work with that, and we'll find that in certain situations it makes solving problems where you're asked to calculate the electric field from a charge distribution much easier than having to go through the full integration that we were doing for charge distributions in chapter 5. Okay, so we're going to introduce a concept called electric flux, which is just the electric field going through a surface. And so we saw that in this demo, where we had this spherical surface and the electric field lines drawn on it. So just to remind you, in chapter 5, when we introduced Coulomb's law, we said if we have a point charge, it will produce an electric field. And we can calculate that electric field at any point in space. And so now we want to do that in reverse. If we know the electric field at some point in space, right over here, if we know that the electric field there is pointing, say, up and to the left, can we tell what charge distribution is producing that electric field? What do you think? Could there be a positive charge down here producing it? Yeah? Because that would produce a radially outward electric field. Could there be a negative charge over here that produces that exact same electric field? There could. So just knowing the electric field at a point does not allow you to figure out what charges produced it. However, all right, so here's visualizing different ways that we could have that electric field generated by two different charge distributions. But what if we knew the electric field at all the points around some surface? So not just a single point, but lots of points. Could we determine the charge inside that surface? So for example, if we know that at every point on this, there we go, at every point on this sphere, or in 2 dimensions it's a circle, if we know the electric field is pointing outwards, what do we know about the charges inside of it? They're positive. How did you know that?
Because electric field lines point away from positive charges.
Yes, electric field lines point away from positive charges. That was one of the fundamental properties of our field lines. And so if the field lines are pointing outwards everywhere around that circle, there must be positive charge inside producing that outflow of field lines. Okay, and then you could flip that around. If the field lines were pointing inwards all around this circle, there must be negative charge inside. What if we change the amount of charge inside this? Let's say we doubled it. What would happen to our field around the circle? Yeah?
It would increase by twice as much.
It would get twice as big, right? So if we see a stronger field around this circle, we must be able to conclude that there's more charge inside. Okay, so we're building up some idea that the amount of field lines going through this surface is related to the field inside. So the amount of field lines is kind of nebulous, right? We could count the number of field lines and use that to describe an amount. But I told you before that the number of field lines that we draw is arbitrary. it should be proportional to the amount of charge. So if we have a diagram with 1Q and 2Q, we should have twice as many field lines coming off the 2Q than the 1Q. But whether that's 4, 8, however many we draw, it's arbitrary. So we need a way to quantify this if we want to make it more mathematical, and that's what we're getting to. All right, so if we double the strength of the field lines, we must have double the charge inside. Now, knowing what the field is around a surface can be extremely helpful in inferring what the charge distribution inside that surface is, but only when the geometry is of that surface is appropriate. So for example, if we have some circle here, I'm going to work in 2 dimensions at the moment. If we have a circle here with field lines leaving the circle all the way around, what do we know about the charge inside? It's positive. Okay, we don't really know where it's located, but what you do notice is that the field lines, they're different strength at different points. They seem to be stronger here than they are way up here. And they're not pointing radially outward like before. So it's probably not just a single positive charge in the middle. Okay, it's something else. It's hard to tell what it is. But if we took a surface that is a rectangle here, and we knew these field lines passing through that rectangle looked like this, can you get any sense of what the charge distribution inside this rectangle might look like? Any thoughts? Hadia?
The field lines, they're moving radially away from the charge, so they must be organized in a horizontal way. Like there must be like placed in a sequence.
Okay. So because field lines radiate outwards, in order to have these field lines pointing straight up and straight down, like they're shown, our charge must be distributed along a line with some symmetry, some translational symmetry in order to get this. And in fact, that's what we have here. If we were to pull back the curtain and look at what charge distribution is creating these fields, it's a line charge. So we call it a line charge because it's a line of charge. Something like if you had a wire that you put some charge onto and it spread out across the wire, that would be an example of a line charge. So we can figure that out if we know the electric field along a surface that matches the geometry of the charge distribution that it contains. But we really can't figure that out as easily if our surface that we know the electric field along is differently shaped than the charge distribution. Okay, so this is all a precursor to what we'll introduce in a minute, which is Gauss's law. But before we go on and talk more about electric fields and electric charges, let me introduce Gauss's law for shopping. So let's say you wanted to figure out how much stuff a store sells. So maybe you're doing some sort of census for the tax collecting for the city or something. You have some stores like Walmart here that sell a lot of products. And then you have these like boutique shops that don't move nearly as much inventory. So you could ask for receipts or go into the store and monitor the cash registers and see how much stuff they sell. Alternatively, you could assume that the more people go to the store, the more stuff they sell. And so rather than go into the store yourself, you could just monitor how much traffic goes in, right? And infer from that how much stuff they sell. Now, in order to do that, you'd have to observe all the entrances. So if you have like a mall, it's not enough just to stand at one door and measure how many people come in, because there might be people coming in a different door. So what you'd have to do is you'd have to mark out a perimeter that goes all the way around. And if it were a mall, you could do that perimeter near the building and count how many people go in. Or you could do the perimeter further out, like around the parking lot, and count how many people come in. And the idea is that either way, you're measuring the same thing. How many people are going into the store that's inside that perimeter? Now, if you were to go inside the mall, back when people congregated in malls, and you were to draw a perimeter like this that didn't include the store that you were measuring, you wouldn't measure people going in. People might cross the perimeter in one direction, but then they'd immediately leave in the other direction. So you get no influx of people. Okay, and so this is sort of the idea of what we want to do with electric fields. That's like the people going into or coming out of a charge. Charge in this analogy is our store. Okay, so it's important that if we want to infer how much charge is contained inside a surface, that our surface be closed, that it completely surrounds some volume of space. Just like if we want to measure the people going into a mall, we need to monitor every single doorway. Okay, so for example, here's just a bunch of charges drawn at random. If I wanted to relate the field through a surface to the charge enclosed, and I draw some surface that only encloses some of those charges, only the field lines produced by those charges are going to have a net outflow or a net inflow through the surface. If you think about the field lines, let's say from this charge, they're going to radiate outwards. And if they cross into our surface on one side of it, they're going to go out the surface on the other side. And so if we added up the field lines all around, and we counted the outgoing ones as positive and the ingoing ones as negative, any charges outside of our surface wouldn't contribute at all to the field, to what we're going to call the flux going through the surface, the field lines going through the surface. Okay, so there's different types of surfaces we could draw around some of these charges. And if we were to count how many field lines pass through those surfaces, how do you think they would compare between these two diagrams? Assuming I draw the same number of field lines from each charge, would I have more field lines going through the sphere on the left or the box on the right? Ella?
Would it be the same because it was the same amount of charges in both?
It'll be the same because we have the same number of charges enclosed in both. So if I draw, let's say, 8 field lines coming out of every charge, and there's 3 charges in both, we have to get 24 field lines coming out of each. Right? Doesn't matter the size or the shape of the surface. What matters is how much charge it encloses. Okay, so we don't care about these charges that aren't enclosed, because the field lines they produce will go in and then out of our surface, so they won't contribute to the total flux through the surface. But what we're developing is some rules. And so we need to clearly identify these rules that we're conceptually developing. And so here they are. Positive charges inside a surface, and by surface I mean a closed surface, so it completely encloses some volume, will produce a net outward flux through the surface, because the field lines point outwards. So they have to go out through the surface. And the corollary is true. Negative charges will produce a net influx through the surface. Rule 2, charges outside the surface don't produce any net flux through the surface. They may have field lines that go in through one side, but they're going to come out through the other, and so they have no net effect on the flux going into or out of our surface. And finally, rule number 3, the net electric flux is proportional to the total amount of charge within the surface, but not the size of the surface. Okay, so the flux is this term that I'm starting to use. That's somehow a measure of like how many field lines go through our surface. Okay, so we'll have a mathematical description of that here. We call it phi. So the Greek letter phi, usually capital. is used for flux. And the flux can be written as the electric field dotted with the area vector integrated over the whole surface. We'll get back to what that means in a minute. But what I'd like to do is try to develop that a little bit more before we get into the mathematics of it. Okay, so let's just review the rules. Positive charges produce a net outflux of electric field lines through a surface. Corollary to that is negative charges produce a net influx, and you can see that in these diagrams. Rule number 2, charges outside of a surface don't produce any net flux through the surface. So, for example, we have this positive charge outside of our circle here, and for this highlighted purple region, the field lines are going into our surface. But if I extended those field lines, they all have to exit on the outside. Now, one thing that we can note is that in this purple region where we have an influx of field lines, we'd call that a negative flux. Flux is defined as positive when it goes outwards. The field is stronger here because the field lines are more dense. But what do you notice about the area of the surface that has an influx compared to the orange area, which has an outflux? Yep, is it Colton? Dylan, sorry.
The field lines are more concentrated.
The field lines are more concentrated in the purple region. And what can we say about the size of the purple region?
Smaller.
It's smaller. And so that's actually a general relationship. Smaller surface that has an inflow, but stronger inflow. So maybe the product of those two things sort of is a constant, right? And in fact, that's exactly what happens. We can see that the field lines that go in must also go out, but we can also think about the electric field, not the lines, but the electric field vector. And if I just plot the electric field at lots of different points, I can see that in this region here, the field vectors are bigger, they're longer. And out here, they're much smaller. But out here, I'm further away. And so the product of the field and the area, which comes into play in the flux, out here is the same as it is closer in. Closer in, we have a large field in a small area. Further out, we have a small field in a large area. So those two magnitudes are tracking. Okay, rule number 3. The net electric flux through a surface is proportional to the amount of charge enclosed, but not the size of the surface. So if I draw a circle around a point charge and count the field lines that pass through that circle, it doesn't matter how big that circle is. We'll have the same number of field lines, because field lines just go on forever. Okay, so making the surface smaller doesn't change the flux through it if it doesn't change the amount of charge enclosed. Okay, so just to be clear, I'm using the term surface and area even though my pictures are just lines. Of course, in the real world, everything's three-dimensional. So when we talk about these surfaces, they're actually shells, spherical shells or boxes that enclose some volume. But in the pictures, I'm just drawing cross-sections. Okay. We can also think about this in terms of the electric field as opposed to the field lines. So out further away, we have a smaller electric field passing through a bigger surface. And as we get closer, the field increases because it's proportional to 1 over r squared. But the area decreases because the area is 4 pi r squared for a sphere. So those r squareds in the numerator and denominator would cancel out. Okay, so just there's many ways to see the same result, but we have these 3 rules that we use with electric fields when we talk about flux. Okay, so these are the 3 rules. Positive charges produce outward flux, and vice versa. Charges outside our surface don't produce any flux through a closed surface, and the total net flux through a surface is proportional to the charge enclosed, but not the size of the surface. Any questions about those rules? Dylan?
With the more concentrated field lines through smaller surfaces, it doesn't affect the charge, but does it affect like the magnitude?
So does more concentrated lines through a smaller surface affect the magnitude of something? It's the magnitude of the electric field. If you put a charge there, it would experience a greater force. But if you were to fill the volume with charges, there'd be fewer up close than there are further away, is sort of the trade-off there. Okay, so let's do another example of flux. You can use your phone and scan in this QR code. And what you're going to get is a dipole distribution, so positive and a negative charge with the electric field lines drawn. And there's a couple things that I want you to pay attention to. So the first is, in the middle of your phone, you'll see a little white ring with a white arrow pointing perpendicular to that ring. So as you rotate your phone, that arrow will stay fixed. You'll also see some yellow arrows at the ring. Those yellow arrows represent, sorry, I have to turn it sideways. Those yellow arrows represent the electric field calculated inside that ring. And the stronger the electric field, the more arrows will be shown. So you can bring your little circle close to the charges, and you should see a lot of yellow arrows. Further away, you should see fewer. And the other thing to note is there is a number right up here. It says phi is some number of voltmeters. That is the flux through that white circle. Okay, that is not a closed surface. It's just a part of a surface. And what I'd like you to do is to try to figure out some relationship. We've got this fixed area disk, or this ring, okay, that encloses a fixed area. And we're able to see the flux through it as we move it around. We can see what the electric field lines are from this charge distribution. So see if you can work out what the relationship is between the strength of the field, the orientation of the field. See if you can make this number go negative. And think about, what does that mean? How do you make it go negative? What does it mean for it to be positive, and what does it mean for it to be negative? So I'll give you a couple minutes to play with that, and then we'll discuss. Once you start getting some ideas, discuss them with your group to see if you can come to a consensus faster. Yeah, it's really small. It's far away. So you might just want to get the eye.
change from positive to negative. So it's the like so it's like the opposite. It changes the area from place to like
Positive or negative.
So the arrows are pointing.
I guess the arrows are like I got negative around positive and positive around negative.
As you move your phone closer to it, it should get bigger.
Yeah, to make it the positive, I got it. It's like near the positive right close to it, but not that. So like if you go like near or whatever, you get like a pretty big charge near it. At it. Yeah, that's near the positive. Yeah. Near the charge.
It's hard to read here.
Trying to get towards it. There's less. This one
Oh wait, depends on what direction the vector is.
Okay, let's see if we can write an expression for phi. What are some of the things that you noticed? Yeah, Hadia?
What the ring was like parallel to the field lines, then it was 0. The flux
Okay.
was 0. It was perpendicular to reach the highest point.
Okay.
And depending on how you move the phone, towards right or left, if you pointed the phone away from the positive side, it was a positive magnitude. If you pointed it towards the positive charge, it was negative.
Okay, great. There were a lot there to unpack. So the first thing was, if you take the ring and you put it parallel, like in the plane of the field lines, you're getting a very low number, or 0, because there were no field lines passing through it, because it was not oriented where it could catch the field lines passing through. Okay, so that is correct. So the orientation matters. Also, what about the strength? How could you make it as large as possible? Bella?
If you bring the ring closer to the two charges, and then when you bring it out, it gets.
Okay, so closer to the charges, the electric field is larger. So it depends on the magnitude of the electric field. One thing we didn't get to play with was the area of the ring. But what do you think would have happened if we doubled the size of the ring? More flux would get through. So we would double the amount of flux. So we can put that together in an expression that looks like this. We could say the flux is proportional to the electric field that passes through it, and it's proportional to the area of the ring. And we've got this little dot. What is that? That's the dot product, right? The dot product tells you how aligned two vectors are. And if the vectors are 90 degrees apart, the dot product gives you 0, because they're not aligned at all. So that's going to account for the orientation. So if your ring is oriented in the plane of the electric field, then no field lines can pass through it. That dot product must be 0 then. But if you orient it one way, the field lines pass through in one direction. If you turn your phone 180 degrees, it's going the other direction. That's going to give us a positive or negative sign on that dot product. Okay, so the electric field vector, we've talked about that. We have a sense of what that is. The direction of the electric field vector is the direction that a charge would feel a force if you were to place it at that point. What is the area vector? How can I make area of vector? Area is usually a scalar. Any thoughts? Yeah.
That's the vector normal to the area.
So it's the vector that's normal to the surface. So if our ring is like this, we could draw a normal. In fact, there was a little white arrow drawn that was just fixed. It wasn't changing at all, and that's because the orientation and size of our ring wasn't changing. That was the area vector. Okay? And so when the electric field is along that, we're going to get a positive flux. When it's anti-parallel, we're going to get a negative flux. And when they're 90 degrees apart, then the field lines aren't going to go through the area. They're just going to go above or below it. And we'll get 0. Okay, so that's an expression for electric flux. Here's a picture showing that if we have some area, now we've got the area vector drawn in on this diagram. Here we go. That area vector is always perpendicular to our surface. So as we tilt our surface, that vector tilts. And when it's 90 degrees, the dot product of E, pointing to the right, dotted with...
4 degrees right now.
Oh, that's cool. With the area vector pointing up, that would give us 0. So in general, the magnitude of, well, the value of the dot product is E times A times the cosine of the angle between them. Right? And so it's a little tricky because you might look at this and think like the field lines are horizontal, the box or the square is horizontal, so the area between them is 0. But that's not how we define the direction. The direction of the area vector is perpendicular to the surface. And that will give us 0 flux when it's aligned like this on the right. Okay. Now it may be the case that at different points along a surface, the electric field has different strengths. So we can't really just say there's one electric field that we multiply by the entire area. We might have to break our area up into little pieces and calculate the flux through each piece. And when we do that, that's integration. Okay, so we can write this more generally as the flux is the integral of the electric field at a point times the area vector around that point. And then when we just add up across the entire surface, that's the integral here. And that's how we will calculate the flux through a surface. If it is a closed surface, it's going to obey those rules that we had, that it's going to depend on the charge enclosed. We were not dealing with a closed surface in this example. We just had a little hoop. So let me do this. I'm going to skip that for now. So let's put all this together. So our definition of electric flux is now the integral of the electric field dotted with the area. Our rules for electric flux said the total flux through an enclosed surface must be proportional to the charge enclosed. And when we write this out, the electric flux, let's use this definition up here to say that E dot dA, that's the electric flux, is proportional to the charge enclosed. And I put this little circle around my integral. That's a symbol that means we're integrating around a closed surface. And it has to be closed because we're talking about the enclosed charge. What does it mean to have enclosed charge if your surface doesn't enclose some volume? Okay, so what we'd like to do to turn this into a mathematical expression that we can use is just figure out what this constant of proportionality is. And one way to start on that is to consider the dimensions. Electric field has units of newtons per coulomb, because it's the amount of force per unit charge that a test charge would feel. Area is going to have SI units of meters squared. So on the left side, we have like Newton meters squared per coulomb. And on the right side, we've got coulombs. Whoops. So that tells us something about the constant of proportionality. If we put in a constant of proportionality, it has to have units that make this balance. Okay, it's going to have units of Newton meter squared per Coulomb squared. We've actually seen a parameter already that has those units. We haven't been dealing a lot with numerical problems, so we haven't really thought about units too much. But epsilon naught was that term that appeared. We said K, the constant of proportionality in Coulomb's law, was 1 over 4 pi epsilon naught. And I said, we'll talk about why we write it that way later. Well, that epsilon naught has units of Coulomb squared per Newton meter squared. So that's interesting. And let's see if we can figure something out from that. So let's figure out the electric field from a point charge. That's easy. We did that last week. In chapter 5, we learned that the electric field from a point charge looks like this. So 1 over 4 pi epsilon naught, that's just the constant K, we were calling it in chapter 5. And then the charge producing the electric field divided by r squared. And it's radially outwards, so we've got this r hat, right? This is basically Coulomb's law divided by the test charge. Let's see if we can use this concept of electric flux instead to find it. So I'm going to draw a sphere around my point charge. It's a sphere because I expect the electric field to be spherically symmetric. So I want to match that geometry with the surface that I draw. And now I know that the field is going to radiate outwards. So the electric field on the surface of that sphere is going to point outwards, and those are the red vectors. And what I can say is that the left side over here, E dot dA, the electric field should have the same magnitude at any point on this sphere, because every point on the sphere is equidistant from the charge. And so the magnitude is 1 over 4 pi epsilon naught q over r squared. Right, that's what I expect it to be. But importantly, it's constant everywhere, just because of the spherical symmetry of this problem. The area of this sphere is 4 pi r squared. This comes from geometry, the surface area of a sphere. Therefore, the left side of this expression, if the electric field is constant, magnitude everywhere, and it's always pointing outwards, and our area vector we define as pointing outwards as well, then this dot product is just E times A. The electric field at a distance of r times the area. When I integrate that electric field is constant, I can bring it outside the integral. And the integral of the area is just the total area. 4 pi r squared. Okay, so this term on the left, the integral of E dot dA, just becomes 4 pi r squared E. Right, the electric field is constant, so I pulled it out of the integral. 4 pi r squared is just the total surface area of my sphere. That's what integrating the entire area means. So that's got to be proportional to the charge enclosed, which is just little q. And if I rearrange that, I can say that the electric field, if I divide both sides by 4 pi r squared, must be proportional to q over 4 pi r squared. Well, I can compare that. I can compare that to the expression that I've got from chapter 5 that said the electric field was 1 over 4 pi epsilon naught q over r squared. The difference between these two expressions is a factor of epsilon naught in the denominator. So that's our constant of proportionality. And what that lets us do is it lets us write this expression out completely, no longer just as a proportionality, but as a complete expression. And it's really important this is one of the four most important equations of electricity and magnetism. It's called Gauss's law for electricity. We will later have a Gauss's law for magnetism. And it turns out to be very useful when we have certain symmetry properties that we can exploit. This problem was spherically symmetric since we had a point charge. So let's just do a couple examples of using Gauss's law. First, let's find the field inside and outside of a uniformly charged insulating sphere. Okay, so that is drawn over here on the left. Uniformly charged means the charge is distributed evenly through the entire volume. Okay, so it's not just a point in the center. Okay, so we could do this using Chapter 5 principles, and we could define a little differential volume and integrate. And I know that everyone would love to do that, but we're not going to. We're going to use Gauss's law. So the first thing we're going to do is we're going to sketch a spherical, what we call a Gaussian surface. This is our closed surface. And if we want to calculate the electric field inside the charge distribution, we should draw that surface on the inside. If we want to calculate what the electric field is on the outside, we should draw it bigger and have it on the outside. Okay, so here I've sketched it in blue, and I've drawn sort of the electric field lines pointing radially outward through that surface. So let me switch over, and I will work this out then the rest of the way on the iPad. So the charge is spread around. I've got this spherical surface, and I know that from symmetry, the field should point radially outwards everywhere and have the same magnitude at all those points, right? Because I could rotate this diagram, it wouldn't change anything. Okay, so the magnitude of that electric field, I'm going to call E of R. It's going to depend on how far away I am from the center, because the further away I get, the more charge is enclosed. Right? Remember, this entire volume is filled with charge. Okay, so I'm going to say that the enclosed charge is equal to the flux through the surface. Gauss's law. It looks like this. My diagram is going to tell me how to write the left side of this expression. So for the left side, I'm going to have the electric field that I identified leaving the surface, E of R, and at any little point with an area dA, let me write that in a different color so we can see it. If I have some little chunk of area dA, the outward normal is in the direction of the electric field. So the dot product is just going to be E times dA. The cosine of phi, that phi is 0. They're in the same direction. And I'm going to integrate this around the entire surface. But the electric field is constant, so I can bring it out, outside the integral. And what is the integral around a sphere? The area integrated around a sphere. Just the surface area of that sphere, which is 4 pi r squared. Okay, and let me make it clear that I'm measuring r here from the center. And this diagram is going to be useful regardless of whether I'm measuring r inside the sphere or outside the sphere of our problem. Because our problem involved the charge being spread out over some sphere, and I had to calculate the field inside and outside. What's different? depending on whether this Gaussian surface that I drew encloses the entire spherical charge distribution or just the inside part of it, is the amount of charge enclosed. Okay, so the right side here, I have to work out. Okay, so if R is greater than big R was the size of my spherical distribution. So maybe my spherical distribution is small compared to big R. Then my surface encloses all of the charge. And that charge enclosed is just the total charge Q. Okay, so I can write Gauss's law like this and solve for the electric field at a distance r is Q over 4 pi epsilon naught r squared. That's just the magnitude. I already know something about the direction. I said it was pointing outwards, so let me add that in. It's radially outwards. And let me remind myself that this is only if I'm enclosing all of the charge, if I'm considering a point that's outside of my charge distribution. But I also want to consider what the field is on the inside of my charge distribution. So somewhere between the surface of my sphere and the middle. If that's the case, not all of the charge is enclosed. The amount that's enclosed, so the fraction of the charge that's enclosed is, and maybe I should draw a more careful diagram here. If this is my charge distribution, and it has a radius big R, and then my Gaussian surface is smaller than that and has a radius little r, how do you think I could figure out how much charge is enclosed in that smaller volume? Dylan?
Maybe find R and then cut it in half.
Okay, I might be able to do it if I made R like half as big.
I don't know if they're the same.
If I made it half as big, I think it would have like a quarter as much charge because of the way that the volume scales are 1/8. Let's see. Let's say this. Let's say the charge enclosed divided by the total charge is equal to the volume enclosed divided by the total volume, because the charge is uniformly distributed. Okay, so the charge enclosed is Q over V times the volume enclosed. Q over V is the charge density, how much charge per unit volume we have. Okay, and I know what that is because the charge Q is uniformly distributed over a volume of 4/3 pi capital R cubed, right? That's the volume of my spherical charge distribution. The volume enclosed, actually let me change the color of this to match my diagram. The volume enclosed is the volume of this smaller surface. It has a smaller radius, little r, but it's also a sphere. So the volume of the sphere is 4/3 pi r cubed. And what we see is the 4/3 pi's will cancel. And we're going to get Q times little r cubed over big R cubed. And that's what we're going to use for the Q enclosed. So all that's going to change, I'm going to get the same result that I had here. I'm just going to change my expression for Q. So let me rewrite that because the steps are all the same. I will erase the Q and I will replace it with Q times R cubed over big R cubed. And I see that this r squared will cancel 2 of those. And this will look like q over 4 pi epsilon naught over times of r over r squared. Okay, so this is for r less than big R. Okay, so we were able to solve this without having to do real integration. Our expression had an integral in it, but because we chose our surface such that the electric field was constant over that surface, this integral really was just giving us the surface area of a uniform object. And we could just use algebra to work out then what the electric field must be in order for that to work out. So we're going to do more problems on this next time, but I want to leave time for our quiz. So if you put away your notebooks, pretty much everything but a pen. Can I ask the LAs to help with the passing them out? And so the way this is going to work, the quiz is double-sided, but you only have to do one side. So look at both sides, decide which side you want to do, and then just do one side. Do not submit both sides. Do your work. You have about 20 minutes. When you're done, take a photograph with your camera and upload it into the in-class quiz chapter 5 assignment in Canvas. If you finish early and you want to leave, as long as you're not sitting in the middle and have to ask people to move, you may leave. But for those of you in the middle, I would like you to stay until you have a clear exit path. And at least just for today, please turn in your quiz up here. So I want both the electronic copy uploaded, and just as a backup, I'm going to take the hard copy. And once I have more confidence that the electronic uploads are working, I may stop collecting the hard copies. Any questions?